Hello everyone, and welcome back. Today we're going to continue our exploration of the R programming language and go through some graphical representations of data that you might want to consider using, especially if you're doing an introductory level of statistics or data analysis. So the first thing that I want to show you how to do is to create a one-dimensional line plot for a set of univariate data. Although this type of plot probably isn't going to be used in professional representations of data, it gives you a couple little bits of framework that you might want to use in other more advanced techniques. So the first thing that we want to do is first off figure out what we're exactly going to be able to plot. So what I've done here is I've just read in a comma separated value file called patient data, which I've already created. And in case you don't already know what this file is, it's just a set of patient numbers, systolic blood pressures, ages, heights, and weights. So let's assume that we, for example, want to create a line plot for the height of this data set. So the first thing that I need to do is first off figure out, okay, well, how many height values do I actually have to work with? So I'm going to call this little n for my sample size, and this is going to be the length of the vector, my data, $sign, and whatever category that you want to extract from this data set, and I'm going to be looking at the height values. So notice that according to this environment, we have 15 height values that we're going to be plotting on a line plot. So the next thing that I want to do is, since we're doing a one-dimensional plot, we need a second dimension to sort of create a 2D representation of that one-dimensional view. So since we're plotting along, let's say, the horizontal x-axis, there's not going to be any y values, so we can default those y values to be equal to, say, 0. So let's create a new vector, let's call it y, and let's replicate 0 15 times. So keep in mind, n is the length of the vector, and we're going to have a bunch of zeros. So 0, 0, 0, 0, 0. So we're going to have height 1, comma 0, height 2, comma 0, height 3, comma 0. So we're going to be plotting these two-dimensional points on a one-dimensional line. So once we have those y values constructed, then we can use the plot command, which is going to take two inputs. So the first input is going to be the x values, so my data, and then the height values. And then the second dimension, which is going to be the y values, which is a bunch of zeros since this is a univariate data set. And then we might want to create, for example, a title of this plot. So in order to do a title for this plot, you would do main is equal to double quotes open, and then line plot of patient heights, and then close double quotes, and then you can add a couple other things. For example, you can do an X label. For example, the X label is going to be the height, and we could also put, for example, in centimeters to advertise what units we're actually plotting. So once we give that a run, you will have this in the bottom right hand corner under the Plots tab of your R environment, and that is the plot line plot for your patient heights. Now, this is probably not the most prettiest of graphs. A better alternative would probably be a box plot. So in order to do a box plot in R, it's going to be very similar structure to a line plot. So this is going to be box plot open parentheses, and then we're going to be plotting our data. So let's say my data, and let's do again the height values. And this is, for example, let's do a horizontal box plot. So horizontal is going to be equal to true. You can also say horizontal is equal to false, which will do a vertical box plot, which is perfectly okay. And then we can go ahead and give this box plot a title. So again, main is equal to box plot of patient heights. And then we can add a couple other different types of things as well. For example, we can add a X label, just like we did before. And again, this is going to be heights in centimeters. And we can also color this box plot a different color. For example, if you want to color it green, we can use COL equals and open double quotes, whatever color you want. And R has a family of colors that you might want to consider. So once we give this a run, this will create a box color for your dataset values. Now, if the box plot command finds any outliers in your data set, it will throw little circles around the points in your box plot, but I do not see any circles in this box plot, therefore the algorithm is not picking up on any outliers of the data set. Now, of course, that doesn't mean that there are not outliers in my heights data set. It just means that this algorithm under box plot is not able to find any. Now, although we already know how to do a box plot for a single set of univariate data, it's often common practice to compare different types of values to sort of see if the means are significantly same, if the variation is significantly same, or just if you just want to compare these sample data sets to one another for whatever purpose. So it's often important to look at several different box plots in the same exact graph to sort of get a side-by-side comparison of what's going on. So let's assume that we want to compare systolic blood pressures, heights, and weights on the same exact graph of, in particular, 3 box plots. So what I want to do is I want to create a set of data. I'm going to call it box plot data or BP data. And this is going to be a data frame containing whatever values that you want to compare. So for example, I want to compare, for example, my data systolic blood pressure, my data, and let's look at the height. And then lastly, my data, and let's, for example, look at the weight. So that's going to create a data frame, which is, of course, a subset of the original data. So systolic blood pressures, heights, and weights. And let's assume that we want to create 3 box plots, one for data set 1, 2, and 3, respectively. So in order to do that, I can easily call the box plot command, so box plot, and then open parentheses BP data, that data frame that I want to analyze here. And let's assume that I want to again do a horizontal box plot. So horizontal is equal to true. You could do false if you want vertical. And again, this is going to be main is equal to box plot of patient information. And keep in mind that all of the data inside of this data frame has their original units. So for example, we have systolic blood pressure in millimeters of mercury, height in centimeters, and weights in, say, kilograms or something like that, right? So although this box plot is going to be useless, it's going to give you at least the main structure of how to use box plots. So let's assume that you want to throw in some names here. So keep in mind, this is going to be a matrix of 3 columns. Column 1 is systolic blood pressure, column 2 is height, column 3 is weight. So we're going to have also different columns associated to the labels and also the colors if you want to add that here as well. So the first name for the first column is systolic blood pressure, and the second name is going to be equal to height. Don't forget your double quotes. And then the third column is going to be equal to weight. And on the next row, let's do colors just for a little bit of entertainment. So let's do light blue for systolic blood pressure, light green for height, and let's do tan 1 for weight. And keep in mind, the columns in this vector, which is typically represented by C open parenthesis, is in the same exact order for which your data frame is given in. So once you do that, that's going to give you 3 box plots that are all horizontal for each of them. If your labels do not come up, that's just because your viewing window is a little bit large. So of course, stretch that out in order to see all of your labels here. So notice that my orange is significantly less than blue or green, and green appears to be the highest. But notice that they have the same exact units in their original spectrum, so it's probably not even fair to compare each of these. But it's important to note, look at this little blue box plot. Notice we have a couple errors hanging out in the upper region. That means the upper 2 systolic blood pressures appear to be outliers. So you may want to consider removing those from your data set if you want to do some analysis on these data sets, of course. Now, as I already mentioned, analyzing box plots where they have different units is highly misleading. So you probably want to normalize these data sets so you can unbiasedly compare each of them. So we're going to be normalizing the data sets, i.e. no units. So one of the most common ways is to take the z-scores of all the values and compare the z-scores for each of the data sets, i.e. create box plots for the z-scores of the data sets. So what I want to do is, of course, create a new data frame. Let's call this BP data norm for the normalized version of our BP data, our box plot data. And this is going to be, again, a data frame. And remember, z-score is value minus mean over standard deviation. So we're going to be doing, for example, my data. We're going to start with systolic blood pressure. Systolic blood pressure minus the mean of systolic blood pressure. And then over the standard deviation of my data, systolic blood pressure. And that's going to be the first value. And then we're going to do the same for the height. So that's going to be equal to my data height minus the mean of my data height, and then over the standard deviation of my data height. And then I'm going to do the same for my weight. So I'm going to do my data weight minus the mean of my data weight, all over the standard deviation of my data weight. And that's going to be our data frame. So if you give this a run, so BP data norm, that should be giving you the z-scores of all of your data sets. That's column 1, that's column 2, and that's column 3 there. You should get numbers approximately between -5 and 5 if you did it correctly. So know that now that we have normalized data sets, creating a box plot for this data is probably going to be a lot more less biased. So what I'm going to do is I'm going to just copy this command for my box plot before, but instead of using my BP data set, I'm going to be using my BP data underscore norm data set and construct a box plot. So if you sort of look at this box plot set compared to the previous one, obviously here we have evidence to believe that weight is significantly less than the other two in terms of its mean. But here we see that actually weight has a higher mean than the other two relative to their particular units. And keep in mind, this is often the case of what you should be doing every time you're trying to compare different data sets with different units. Another type of representation that you probably want to do for numerical data would probably be a histogram. So in order to create a histogram, you need to partition your numerical data spectrum into a set of discrete categories or subsets of your continuous spectrum. So usually the histogram function in R will allow you to choose how many what we call breaks you partition your set into, but you can sort of tinker around with how many breaks you want in order to give you the histogram that looks best appropriate or looks best for your particular data set. So in order to make this histogram look a little bit more useful, what I want to do is create a set of normally distributed data set. So let's create a normally distributed, at least discrete normally distributed data set. And let's call this data set S. So in order to create a normally distributed data set randomly via R, this is going to be R norm, and then it's going to ask you N. That's how many values you want in this particular sample. Let's do 10,000. So 1, 2, 3, 4, 0 is there. Let's do a mean of 124 and a standard deviation of 2.45. So this will probably be a normally distributed set of systolic blood pressures, for example. And now let's do a histogram for this data set and see if it actually looks like a normal distribution. So what I can do is I can do hist and then the vector that you want to create a histogram for, and then breaks. This is going to be equal to how many boxes or bins or sets you want to partition your spectrum into. Let's do 50, so we should have approximately 50 bars. And then let's title it. So this is going to be equal to a histogram for our random sample systolic blood pressures, and then we can add, for example, an X label just as before. So this is going to be equal to systolic blood pressures in millimeters of mercury, and let's also color it as well just for fun. So let's color it orchid. And that's going to create a histogram, although it is not, of course, exactly normal because it's a discrete subset of a continuous spectrum. It does look approximately normal, so that's, of course, anticipated of what the histogram should look like. But usually you should not be using a histogram if you have a significantly small size data set, else you'll get misleading or useless interpretations. As we should already know, you should only be using histograms for numerical data. Let's assume that you have a categorical data set, for example, red, blue, purple, and green. So what I'm going to do is I'm going to create a vector called favorite color, and favorite color is going to be the vector called, let's say, red, blue, purple, and red. Now let's do green. We already did red. So once we have our favorite color vector defined, then we can define our favorite color frequencies. For example, favorite color frequency is going to be equal to, let's assume we had 29 responses for red, 12 responses for blue, 18 responses for purple, and 14 responses for green. So those are going to be our color frequencies. In order to do a bar plot for a categorical data set, what you can do is just call the bar plot command and then do favorite color frequency. And then let's name it. So let's do main is equal to favorite color survey results. And we can add, of course, some labels for it. So to do labels, you're going to call the name names, because it's not an X label, because it's not necessarily a numerical data set. So names is the categorical equivalent of XLab. So this is going to be equal to the favorite color vector, or you could define it directly here if you want to. And we can also color it as well. So let's do color is equal to, and we can color each of these 4 columns. For example, we can do fire brick 3 for the red data set. We can do steel blue for the blue data set. We can do dark orchid 2 for the purple data set, and we can do light green for the green data set. And once we have each of those things and we spelled the word orchid correctly, then it should be creating your bar plot for your categorical data set. Now, bar plots, of course, are not the only way you can represent categorical data. You could also do pie charts. So in order to do pie charts, it's going to be a similar structure to the bar plot command. So the first thing we need to do is, of course, if you want to put the percentages associated to each of the categories on the bar plot, you would have to create a vector for that. So let's go ahead and do that first. So lab percents is going to be equal to, and let's assume we want to round to the nearest percent or something like that. So what we're going to do is we're going to round the favorite color frequency divided by the total number of frequencies. So that's going to be the sum of the favorite color frequency vector. So that's the sum of all of the frequencies. And we're going to, let's say, multiply that by 100 to give the answer as a percent. Right. So that's going to give us all of our percents. And then we're going to put the favorite color, we're going to paste that onto the lab percentages. So we're going to paste the lab percentages onto the favorite color vector that we've already defined. So lab percents on top of that, and we're also going to throw a percent sign behind each of those labels. So it says favorite color, lab percent, and then the percent sign. So for example, red 15%, and then the percent sign, or favorite color red 15%, as it's listed here. So that's going to create a string on our display. So in order to construct this little pie chart, the function is going to be called pie, and then we're going to again be calling our favorite color frequency as our data set, and then of course we can create a label or a title for this, and this is going to be our favorite color survey results. Again, we're just displaying them in another way. And then the next thing what we're going to do is we're going to do labels is equal to, and then we're going to combine the favorite color together with, and let's put a space in between these things, and then our lab percents. And then we can color them in a similar way we did before. So what I'm going to do is just I'm going to color or copy that color vector that I defined before, and this is going to define your pie chart for your categorical data set, which is just an alternative representation for your box plot. Sometimes it gives you a little bit different insight compared to the bar plots that we had before. Up to this point, you should be able to construct graphical representations of data both for univariate data and also bivariate data via, say, scatter plots or something along the sorts. But what if you have a data set that is multivariate, in particular more than 2? For example, if we want to compare 2 different personalities where those personalities are characterized via the Big Five model: openness, conscientiousness, extroversion, neuroticism, and agreeableness. How would you sort of compare that? Because box plot obviously isn't going to be as easy to read for a data set that has more than one variable. So one way you can actually analyze multivariate data sets is with what we call radar charts. So radar charts are actually nicely implemented in the FMSB package. So the first thing that you want to do is install the FMSB package if you want to do nice radar charts. And then once you press enter, it should have you some display here in this bottom little terminal. And tell you that it has installed quite nicely. So once everything is installed, then you need to import all of the things in that library. So we need to import the FMSB library, and once it is imported, you can use all of the functions that are available in that particular library. So let's assume that we want to place a radar chart of person 1's personality and person 2 personality on the same plot and compare their personalities via radar charts. So once you have your two people's data set here, you could also have person 3, person 4 down to person 50 if you want to. It will look a little bit clustered, but you can do it if you want to. So what I want to do is I want to bind these two vectors together into a matrix. So I'm going to say my data is equal to R bind, which is short for row bind. You can also do C bind for column bind if you want to combine some columns or glue them together into a matrix. So what I want to do is R bind person 1 and person 2 inside of the same exact vector. So if you display this is going to create a matrix with those two rows glued together. So the next thing I want to do is I've already created columns associated to the names of each of these labels. So what I want to do is say, okay, the column names of my data are going to be equal to the things that are associated to the vectors in PCAR, or the personality characteristic names. So once I do that and then display my data, notice that I have now assigned labels into this particular structure. So what I'm actually doing here is creating a data frame. Now, in order to use a radar chart correctly with the FMSB package, you need to also specify the maximum and the minimum values associated to each element for each vector in this particular data frame. And you need to have those pieces of information also glued inside to the top of your data frame. So how do you do that? So my data is going to be equal to data frame, so data.frame, and we're going to rbind a set of three things. The first is going to be your maximum vector. So we're going to repeat the value of 10 because 10 is going to be the maximum value for each of these individual personality elements, and we're going to have 5 of those elements. So it's 5 rows of 10. And then we're going to have the minimum vector, so we're going to repeat 0 5 times, and then we're going to have our my data glued at the very bottom of this particular vector. So if we look at this particular matrix, notice that we have a bunch of 10s, that's the maximum for each of the elements. 0, that's the minimum for each of the elements, and then the individual values that we're plotting along each of the vectors is 0 to 10, 0 to 10, 0 to 10, 0 to 10, and 0 to 10. Once you have our data frame looking just like this, now you are ready to construct your radar chart. So what we're going to do is we're going to do radar chart, and then we're going to do my data. And then of course you can add some flavor to this if you want. So the first thing that I want to do is actually just run this just to see what it comes out to. It does display a radar chart, but you might look at this and be like, it doesn't look that nice. So let's make it a little bit more prettier than the default version. So the next thing I want to do is add a little bit of color, and maybe you can guess what these are going to do. So the first command I'm going to call is CGLTY. If you're familiar with LTY, that's of course a line type. And this is going to be equal to, I'm going to set this equal to 1. So once I change that, it changes it from the default dotted line background to a solid line background. And then of course I can add the color to this, but instead of a blue, I can default it to, for example, gray. So CGLCOL, this is going to be equal to gray. That's going to change the background to a little bit gray because I don't want that to sort of interact with my colors for my actual personality pentagon, or polygon rather. The next thing I want to do is the following. I'm going to do PLTY is equal to 1, and then PCOL is equal to vector, a couple of colors, steel blue, and then orchid. So these are going to be the colors in order for which you have defined them inside of your data frame. Steel blue for person 1, orchid for person 2, and then the last thing I'm going to do is I'm going to do PLWD is equal to 1. And that's going to change the line width a little bit. So that's the line type, the circle, and the PLWD, that's the thickness, and these are the colors in the respective order that you have defined them. And of course you can vary these based upon your particular preferences. Now, notice that these polygons are not really shaded on the interior. You can easily change the interior shading for each of these polygons, and again the color spectrums are going to be in the same exact order as before, and you can do that with the PFCOL command. So what I'm going to do is I'm going to call these from RGB vectors, and the RGB vectors are continuous from 0 to 1 for the RGB spectrums. So R, G, and B, so R, G, and B, so this is going to be a blue vector. And then 0.2 is going to be the opacity of that particular object. And then I'm going to do RGB, and then R, and then G, and then B. So it's a mixture of R and B with an opacity of 0.2. And then I'm going to do VL, actually no, I'll save that to the end. Let's just give this a run and see what that looks like. So notice I have our blue region for set 1, and then R, no G, B, so R plus B, so red plus blue gives us this little purple color a little bit, which is actually magenta. And this opacity 0.2, you typically want that to be as small as possible. That's the value for which you can actually see through that, because you don't want it to be totally dark, and then you can't see what's sort of hiding underneath that. And the last thing that you probably want to change is these labels. Look at conscientiousness, it's sort of blurring into your radar chart. So in order to change the labels associated with them, you can do VLCX, and this is going to change your text size for each of the labels. And if you sort of choose numbers between 0 and 1, you can sort of figure out what's best for your actual representation. So this gives us a nice little representation for our radar chart for our personality comparisons for person 1 and person 2. And you can, of course, add several other elements like legends to this if you want. And for all of these graphs, for example, your radar charts, your bar charts, your any charts, you can always export and save as image, and it will allow you to save each of these images on your computer, so you can include them in your text file or your PDF or your Word file or whatever presentation format that you're interested in doing. But these are some of the most common basic elements that you could actually represent data in a graphical manner by. There are several others. For example, the ggplot2 library has so many different functions that we're definitely going to talk about a little bit later on. But these are some of the basics that you definitely should be able to implement, especially in the early stages of your elementary statistics and data analysis careers. I hope you enjoyed, and I'll see you in the next video. Take care.